Okay, we're live.
Yes.
Okay, all right. Good morning, good afternoon, and good evening. I see that there's about 3,000 people here on this call. I want to welcome everyone to this session on neural networks. My name is Haroon. Just a little bit about me before we head into the topic here. I'm a consultant. I've been consulting for several years now, mainly in healthcare. It's one of my passions of mine, and teaching as well. It's one of my other passions. Outside of those two things, I'm a big car guy. You can talk to me anytime about Saabs. It's a dead car brand that you've never heard of. I suppose maybe you've heard Volvo. Anyway, today's topic is going to be about neural networks. So the key idea that I want to partake on you all is neural networks isn't as complicated as it may sound. And I want to break down that maybe that barrier or that gap that maybe you'll see in a beginner in terms of, hey, what exactly is happening in a neural network? So I really just want to focus in on the concept and the idea. I won't go too much into the math here. There is going to be some light math, but I promise it's going to be very light. Really, the focus on this session, though, on this topic is I want participants, I want you all to have a good understanding of what's happening behind the scenes in a neural network. Sound good? Yes, I can include my contact, absolutely. As a matter of fact, I can do that now. So, and let me grab my LinkedIn too for those that would like to do that. So give me 1 second. Yeah, and there's my LinkedIn. Just a note here before we get started. So I really like to have interactive type sessions. So it's not just me blabbing up here. Feel free to come off mute. Don't be shy. You can speak out if you have a question, or if you're more comfortable, you can utilize the chat there. I'll try my best to monitor. But I understand I got to share screen and all these other logistics. So, but I will try my best to monitor that. All right, let's get started. So let me go ahead and share my screen. And I want to share the tab because the tab works, but apparently nothing else. Okay. So hopefully everyone here can see my screen. Again, I think I lost everyone's. If you want to go on screen, listen, we'll bring you on. Looks great. Okay, so we can see it. Okay, great. All right. So this notebook I will be attaching or sending Amelia. This is an oversight on my end, but I can send you this file so participants here can have that if you ever want to refer to it, right? So real quickly, we're going to talk about deep learning. We're going to talk about PyTorch as a tool, and I want to show you how you can take a model that's off the shelf and utilize it today. So essentially, hey, let's create some import statements. Let's initialize some stuff, so to speak, and we can start using a deep learning model within minutes. Yeah. Okay. Why should we even care about neural networks, right? So neural networks is driving all the innovation in next generation technology. What do I mean by that? Self-driving cars, chatbots, so many applications that are being driven by neural networks and deep learning is absolutely critical that even if you don't specialize in it, that you understand what's happening behind the scenes. The famous example here, maybe some of you have noticed, maybe some of you have noted this example, AlphaGo beat Lee Sedol in Go. So that was a really big turning point for neural networks. There's this link here and you can read all about that. There's also some geopolitical ramblings or musings. I don't want to get too much into that, but certainly you're welcome to read some of this. So what is deep learning, right? So deep learning you can think of as a subset of machine learning, which is of course a subset of AI, okay? So here's how I like to give the example of what's happening in deep learning. Okay, So I need to stop share, and I need to share another tab. Share screen, and then share another tab. I need to get, there we go. So I think hopefully everyone now sees a whiteboard, yeah? Okay, so the idea behind a neural network is we want the computer to automatically see or observe what our data points look like. Okay, so here's what's really happening here. In the past, you had an SME here, right? And he's working, right? So give him a little hair. And so he's working, right? And so he has all this data, right? So he's going to put all this data into his fund database, right? And so from here, once he puts the data, he wants to tell the computer, hey, let's pretend we're looking at portraits, right? So if I could draw anything, maybe like a, nope, sorry. Go here, and we have like a portrait, right? Nice portrait, right? This is high quality art here. So, you have your, right? And then this and something like that, right? So you have your portrait, and this SME, this person, he'd go in and he'd tell the computer, hey, this is an ear, right? And actually, let's change color too. Let's get a red. Yeah. So here is something called an ear, right? And so there's some kind of definition involved, maybe some pixels. He tells the computer, hey, look for pixels of these sorts, right? So here's an ear, and here's my eyes, right? And here's my nose, and all these other things. And things I want to refer to here as features. So this SME, this data person, he is manually going in and telling the computer, hey, this is something called an ear, right? And this is something called an eye. And he's manually doing this process, okay? This is called feature engineering. So what makes neural networks so great is, hey, I don't need to actually worry about figuring out what my features are. I can let the computer do it for me, in the sense that now the SME, he can just go in and he can just give it to our model, our machine learning model, and specifically a neural network. And within this model, it will tell us, hey, these are the features that I see. Here's one feature, here's one, here's two, here's three, and it'll give representations of those features. So this is what's really, really cool about neural networks. The computer automatically distinguishes, hey, is this an ear? Is this water? Is this a cat? Is this a dog, right? And it's able to learn that, of course, by the data points that you give it. Let me take a pause here. Any questions so far? Feel free to come off mute. I need to actually check back on the chat. So if there are some questions. Yeah. Yeah, I like sketching. Yeah, I mean, my 5-year-old cousin just laughs at me, but hey, I like it. So other stuff in the chat. Okay, yeah. Again, feel free to come off mute, ask questions. If you can understand this part so far, you're in a really good spot. Okay, so let's go back, and I need to stop share, and I need to. Is this just for pictures, or it can apply? Absolutely, it can apply to CSV. It can apply to any kind of tabular data. Neural networks is very common in image recognition, but certainly you can use this for tabular data. Did you mean to say that learns what is a picture versus that I can tell? Correct. Do you mean to say that the neural learns what is a? So yes and no. Yes, it learns what a cup of water is or what a cat is, but it's up to you, the user, to know what is, of course, a cup of water or a cat. In other words, it knows that, hey, this looks like something, right? And if I give it a comparison point of, hey, this is a picture of a cat, it can tell me with some certainty, with some probability that, yes, I think, for example, 90%, that probability 90% that this is a picture of a cat. Are the data points you refer to in this case are images? They can be. They can be images, they can be videos, they can be, like I said, tabular data. There's no limitation here in terms of what kind of data you have. This is what makes neural networks really cool. Keep the question coming, guys. I really appreciate that. Okay, so let me go back here then and share the screen. Of course, I did it, but I can't remember anyway. Man, it's rough. Okay. Yeah. So really, just kind of a summary here. This SME, he takes in, right? He just dumps in the data before, and he had to say, okay, this is my, ears, this is my eyes, this is my nose. But now it's different. With neural networks, the data, you just kind of dumped it all in, and the machine figures out, oh, it's this. Okay. So the example that I like to give here for neural networks. So I'm a big sports fan. I live in Atlanta, so the Braves, of course, we're the world champions. We're the best, and all that good stuff, right? So one way that I like to talk about neural networks, or at least make it less mysterious, is, hey, let's have a common example, right? So this is going to be the simplest iteration of a neural network that you'll ever see, right? So for this neural network, what we want to say is, okay, let's predict how many wins the Braves are going to have next season, right? And so we want to do that based on the number of fans in the stadium. Okay, so I know this seems a little nonsensical, but you'll see the point very soon. So let's define some things, right? So let's create a list here of possible choices of fans, and let's at the same time create a random weight. What this weight is, it doesn't really matter. It's random. So I just picked a random number here. Okay. So what do I mean by a weight? Okay. So think of the weight as something like a volume knob, a sensitivity knob, right? So if you played around with AM radios, right, it shows you how old I am. So in the AM radios, you have that dial, and of course, you don't have dials now. You just tell Siri, and it does it automatically. But pretend if you did, right? So if you have the dial, it increases or decreases the sensitivity, and that's what really the weight references, the sensitivity of our model. So in the beginning, we're just going to pick a random weight, but I want you to think forward. Okay, this weight is going to be adjusted, either tuned up or tuned down, based on my results. Okay. So here is my very basic neural network. It takes in some fans, and it takes in a weight, and it's going to return me a prediction. You switch back. Is there any questions? Does it take people to teach neural? So yes and no. The example that I'm going to show later on here today, the creator of that model, the ResNet model, they've actually told the computer that, hey, this is an image of a cat, and we're going to use that classification to predict a new picture that it hasn't seen yet. So it's going to make that jump that says, hey, this is what I know looks like a dog, and I'm going to give it a new picture, and it's going to say, hey, this is, in my guess, I think I'm 90% correct. This is what's going to be a dog. Let's see, any for other. So does it take people use picture as example? How about yeah? NLP is a really good example of that. I also have another website that I want to show. It's really cool. It's not NLP, but NLG, natural language generation. And there's a model behind it that basically you can type a few words, and it'll go ahead and create a story for you. It's really neat. Okay. So let's take a look at our neural net in action. Okay. So we got a result of 0.4. So what does this mean? Really, this means, hey, we have a 40% chance of our prediction, right? But that's not really what I want to point your attention to. The point that I really want to emphasize here is there are three things happening here. There's an input, there's a weight, and then there's an output. Okay. So the input in this case was the number of fans, and then we had a weight, and then we had something called an output, right? Whether the Braves will win. this, in essence, is the building block of a neural network, whereby, and I think this is better if I draw this out. So I can stop the share and reshare. Thanks for being patient, everyone, for all the flipping. I guess my computer is special. Okay, so we can go ahead and clear all this. We can just pick a new spot. Oops. Clear. That's fine. So really the point I want you to take here is, hey, we have an input. Oops. We have one input here, right? And that's going to be our number of fans. And we have an output, number of wins, okay? And between these is going to be my weight, okay? And really, this is the basic structure of a neural network, where essentially you have one input, at least a input, and you have some kind of output here. And this output is adjusted based on the weight. So if you're able to follow along so far, you're in a good spot. Of course, it's going to get just a slightly more complicated, but if you can see this picture where you have one input here and an output and a weight, you're in a good spot. All right, let's continue. Let's get it just slightly more complicated. So stop the share and reshare. Okay. So let's expand on our model, right? Let's add multiple inputs and weights. Yeah. So now instead of just having number of fans, let's say, all right, let's have an input of a win-loss record from a previous season, and let's have something like players batting above 300, right? So if you have one player, two player, and three players, right? So we have some more inputs now. Yeah. To combine all these inputs into one output, we're going to take essentially a weighted sum, right? So if you remember way back when, in a weighted sum, we are multiplying different inputs with their corresponding weights, and then we're adding them up, right? And again, this goes back to the heart, the math here of a neural network. This math is not going to change. So what is going to change is the complexity and the number of layers and the number of neurons, right? But this math here, where, hey, if I want to make a prediction, I'm going to take the number of fans and the win-loss, and I'm going to apply a weighted sum. Okay, so let's see this in action. So I have my function here, a better neural network, and again, I want to take a weighted sum of all my inputs. Okay, so essentially, what I want to say is, all right, here's going to be my inputs, and my weights are going to be these guys. And I want to multiply my inputs by the corresponding weight. So for example, this, I believe, will be multiplied by that, and this will be multiplied by this, and so on and so forth. And I'm going to add all those together. So here's our new prediction. So we're a little closer, right? Just slightly. But the point remains that in a neural network, this type of math, a weighted sum, and again, I can clarify here, where we're basically taking these inputs and we're applying a weighted sum. Let me take a pause here. Does anyone have any questions of what a weighted sum is, or how this works? Can you have access to? Absolutely, yeah, absolutely. Would this be considered one layer? Exactly, yep. So this has one, as a very basic example, one input layer and one output layer, right? Right. Good questions. Yep. So again, just to reiterate what we did here, this is a dot product, right? A weighted sum between two vectors. And if you can wrap your head around this mathematically, you've really understood neural networks. You really have. Even the complex neural networks that have multiple layers and multiple neurons attached to them, right? And they have different activation functions. That's the math here is still going to be the same. And when you see, hey, these are computationally intensive, you can try to extrapolate that, okay, even in this basic example, we just have 3 weights, or rather 3 inputs, sorry. When you have multiple inputs and you have multiple layers, this kind of weighted sum math, right, that can be very computationally expensive. So this is where the black box aspect of neural networks comes in. But I'm going to save that for later. Okay. So again, this is the basis for neural networks. This idea of a weighted sum, and I have multiple neurons, and there's some kind of input and some kind of output. Yeah? Let's keep going. So let's get just slightly more complicated here, and let's say, hey, we have a matrix of weights, right? So essentially a matrix here is going to be, you can think of as a list of lists, right? And so what we want to say is, okay, we can get more complex by passing in multiple weights and taking weighted sums of those, okay? And this picture right here is the typical picture that you would see for a neural network, right? And so let's talk about what some of these things are. I don't think I can annotate on this, but anyway, I'll just highlight with my mouse. So if we were taking the same example with the baseball, right? So something like this here at the left, that's going to be your input layer. And the green here would be the output layer, or the number of wins. So what does that leave in between all this stuff here, right? So in neural networks, you are not limited to how many layers that you have in a neural network. So these two here in the middle, these are what you can think of as the hidden layers. Okay, what exactly is a hidden layer? What do I mean by that? It's the layer such that these transformations, the weighted sums, that's where they're happening. Okay, so we can have as many of these layers as we want with different functions. Okay, I'm going to talk about functions towards the end here. But just think about in terms of I have an input here that goes to an output here, which then serves as an input to this output, to this layer, which also then turns into an input to this output. It's this complex model of multiple layers, and that's really what a neural network is trying to show. Let me take a pause here. Maybe some questions. Is the weight sum to a calibration factor? I think that's something slightly different. Although, or maybe I haven't heard it said that as a calibration factor. But I'll have to get back to you on that, James. Yeah, good question. It's the first time seeing that. Okay, so we've talked about kind of the nuts and bolts a little bit of how a neural network is structured. But we haven't actually talked about how it learns, right? So in our fun, simple example here, this is a neural network that only goes forward, right? So it doesn't do something called back propagate, okay? I'm going to explain what that means. Well, let's take this example from where we left off, right? So our model, right, isn't really good if the prediction is flat out terrible, right? So how do we change that? How can we improve our model such that we get a closer prediction, right? So what we want to do here is, as a basic example, we can say that, hey, I want to measure this neural network in terms of mean standard error. And if you're not sure what mean standard error is, or mean squared error, it's this here. So essentially, we're saying the predictions minus our goal and squared. And why are we squaring it? That's just to get rid of any negative numbers that may come out of this. Okay. One way that we can improve our prediction is to reduce our mean squared error, right? So let's think about that. If we have a high amount of error in our model, what we can do, we can't really change the input, right? The data is the data. But what we can try to tinker with is the error. And how can we do that? By changing the weights, right? So this is where we think about that radio knob or the volume knob. We can adjust weights up or down to see if we can reduce the error, right? And in any goal here, we want to get the error as close to zero as possible. So if you were to do this manually, right, I like to call this the hot and cold. So if you were to do this manually, you'd want to say something like, hey, I want to see if I can give my weight here some kind of extra variable. Let's call it a learning rate, right? So I would modify my current prediction based on this learning rate. So in this first example, let's see if we add a factor to our weight here, does that get us closer or farther? So it looks like it gets us slightly farther, a little bit. Yeah, our mean squared, looks like our mean squared error went down. So it gets us slightly, yeah, it gets us a little bit better, right? And we can also try the opposite too, in the sense that, all right, here we increased our weight, essentially. We increased it. Now let's decrease our weight. Okay, so we went further, right? What I'm trying to show you here is this is essentially what's going to happen inside the computer. When we apply a neural network model, we can use back propagation to say, hey, the computer is saying the weights need to be adjusted to this. Let's go back a layer and let's fix it. Let's get closer to our prediction. And how do we get closer to our prediction? It's going to be reducing the error. Let me take a pause here. Should the weight be determined? So eventually, yes. At the very first step, Ling, the weight is going to be just a random number. But as the model runs, it is going to be determined, right? Which weight is going to get us the lowest error. Okay. The most popular way to calculate this error is with gradient descent. Okay. So think of gradient descent, and I don't want to scare you guys, but think of gradient descent as a derivative, right? We're going to take some kind of derivative, and we're going to try to get that number as close to zero as possible, okay? So let's piggyback off our previous example here, where we have a weight, we have a goal prediction of 0.8, and we have an input, okay? So now, let's see what happens when we apply a basic example of gradient descent. So what's happening here? We are incrementally increasing the weight, right? So you can see here that we have a weight. We started off with 0.5. We're increasing the weight, okay? And we're seeing that, okay, as we increase our weight, we are getting a better and better prediction. And we know what direction we're going. This is essentially what happens underneath the hood for a gradient descent. And I want to show this picture right here. This is essentially what's happening. When this slope gets to zero, or as close to zero as possible, that's when you know the error is at its minimum. So a neural network is going to try to find this minimum. It's going to try to find where this error is as close to zero as possible. And again, this would be the slope, and this is a derivative of this line here. I know it's been quite a while for some of you. You hear the word derivative, you get scared. I mean, I do. I certainly do. I like to think I'm good at math, but sometimes I humble myself. Let me take a pause here. Any questions so far? I know I'm kind of going through a lot, maybe a little too fast, but I'd be happy to slow it down. Okay, nothing in chat. Okay, I'm going to keep going. Really, what I want to focus your attention on is this graph here. If there's anything that you take away from this lecture here, it's, hey, a neural network is designed to reduce the error as much as possible. And all the things that are happening inside of it are geared towards reducing this error. Okay? So here's what it boils down to. A bunch of weights used to compute an error function, and there's always a relationship between any weight or error. And really, once you can see this relationship, you'll know that, hey, whatever function I apply, it's going to be to reduce this error to 0. And I have a fun little, if you're a Simpsons fan, maybe. Okay, let me take a quick pause here. Anything that anyone would like me to go over in terms, and of course, there was a request here to make this available, and absolutely, I will make this available. So that's not a problem. You can feel free to review this on your own time if you want to look more in detail here. But anything else I can help clarify in the bring file? Yeah, exactly. It's not. I don't think it's differential calculus. This is just you just need to know enough about derivatives and partial derivatives. I don't think it's differential. Yeah, flashbacks to calculus, man. Getting scared already. Okay. All right. So I've given everyone here a bit more background, I hope, on neural networks and kind of how they work underneath the hood. So now I'm going to shift gears here and demo PyTorch, right, and why it's useful. Okay. Before I do that, though, I do want to share that example that I mentioned earlier. Can everyone still see this infer kit? Because I think I may have. Nope, you can't. So I need to share it again. Chrome tab. Yeah. Again, this is part of the notebook, but it's a really cool example of a deep learning model, right? So you can just type in some text here. You know, I'm big, like I said, I'm a big sports fan. So today is NBA free agency or something. And let's see if it can generate some text. Man, that was really terrible. That was off. The Los Angeles NBA? What? No. Okay, so now it's getting sports. Oh yeah, that wasn't bad. Fill this stadium with a bunch of Bucks fans. So it's like kind of there. Although the Los Angeles NBA, I don't know about that. There's a lot of cool examples here. Let's see if I can. I don't want to get political or anything, but let's say the EPA designated that coal should be, and let's see what it says. Man, that's really interesting. Anyway, this is something that's free. This is app InferKit. It's a really cool way to see a neural network in action. I thought it was really cool, so I want to share it. Anyway, let's get back to PyTorch. So let me reshare here. Okay. So what's so great about PyTorch, right? Here's this website. You can take a look at it. It's really good. In a nutshell, it's just really good. It has great documentation, written very well, and of course, it has the function to offload to GPUs. I just kind of want to show this model here, this diagram here, just very quickly. This would be a typical. This would be a typical way to deploy a model using PyTorch, right? So PyTorch takes something called tensors, right? So after you have these tensors, you've loaded them, and here you're going to train your model, right? And at the same time, you might have multiple computers or multiple GPUs that are training that model, right? So then you have your trained model. After you have your trained model, you're ready to deploy it. So you can deploy it, whichever way you want, in the cloud or on your local server, how have you, and you can essentially start applying it. So pretty straightforward in terms of how to implement a PyTorch model. This is a paradigm in pretty much all of machine learning in terms of, hey, we're going to create a model, we're going to do some testing on it, and then we're going to deploy it. Okay. So here in this part, I just want to show you how very quickly that you can implement this library to do something useful. Okay. So as I alluded to in the very beginning, I am going to take a model off the shelf. And by off the shelf, what do I mean? I mean a model that's already been created by someone. And I can use that model, I can just import it at my whim. Okay. I'm going to take an off the shelf model, and I have a picture of a dog, and I want to see how close or how far this model can get to the picture. Sound good? Okay. So again, I have all this code available. I will have it in this notebook, and I'll send it out. But really, what I want to show here is more how easy it is. You don't really need to know too much about, hey, what's going on, Pythonically speaking. You don't really need to know so much. This is what I think is so interesting about machine learning. As you're going to see here, the application of it is really incredible, and you don't really need to know so much about the nuts and bolts. You need to know enough, but if you get deeper in the field, if you have a passion for neural networks, then that's a good segue to start learning more about the details, right? But in this very beginning stage, if you're new to this, you can see that, hey, I just need to import a couple things here, and here's a list of all the models that I have available in PyTorch. So I have something called an AlexNet, a DenseNet, GoogleNet, all these different models here. I think for this example, I'm going to use a ResNet, I believe. If I just scroll down, an AlexNet, I suppose. Okay. And let's take a look at what AlexNet looks like. It looks like this. So we start off, let's break this down. This model is built on 1, 2, 3, 4, looks like 7, 8 layers here, right? And this 96, that's the number of neurons in each layer. So the 96, 256, 386. This is how this model is structured. These are all the different layers. And it looks like this is the output here, this 1000. We can see the nuts and bolts of it in terms of all the different functions that are applied in each layer. I'm going to pass over that because I don't think it's as important to know in this beginning stage. What is important is, hey, this is what the network looks like, and this is the back end, if you will, of what that looks like in code. Mm-hmm. Okay. Oh, so we're also creating ResNet here too. So again, just to kind of show you what does ResNet look like, right? So this is what we're going to do. We're going to take this picture of a dog. I have this picture of a dog here. Yep. So here's my picture of a dog, right? So I'm going to do a bunch of backend stuff. I'm going to do some pre-processing. I'm going to normalize it. Again, I don't want to put your attention on this part. It's more about, hey, this is all I really need to run a neural network. Okay, and you'll see it's fairly not straightforward, I would say, but the amount of code here is really not a lot. Okay, I do want to spend a moment to talk about each cell. In this cell, we're doing just some pre-processing here. You can see more what the pre-processing entails. So if I say, just know that it's doing some kind of transformation here, okay? Here, we're doing some reshaping and cropping to normalize the input tensor, right? So we need to normalize it for ResNet to understand, to take in the data, okay? And let's go ahead and put it in evaluation mode. Once we do that, we can pass in our batch underscore t, this guy, the one that we just reshaped. Let's go ahead and pass it in. So here's what it looks like, numbers, right? Very exciting. No, exciting part's going to come in a bit. I'm showing you this just so you can kind of see what's happening behind the scenes. These are all the different numbers that are related to this image here, right? Okay. So now we've passed in our image. Let's go ahead and see if this model can compare, right? Can it figure out, is this a dog? And maybe tell us a little bit more information, right? So the creators of this ResNet model, they give a ImageNet classes, right? So I think this question cropped up earlier, whereby, hey, are we having to tell the model that this is, for example, a dog? And in a certain sense, yes, we are having to tell it, and we can tell it, and we can put it into this like a text file here, right? And the idea here, maybe I can open it. Well, I think you should be able to see it if I run the cell anyway. Oh, nope. Here, I want to stop share. I want to open that just so you guys can see that, what I'm talking about. Mm-hmm. And I need to reshare my screen. Chrome tab. Here's what that text file looks like. So it has a bunch of animals, right? And essentially, it's going to try its best to figure out which animal it is between all these animals. Okay. Let's go back to my notebook. Okay. So here in this torch, we have our image, right? And we're going to try to get essentially the best value from that list of what this image could be, right? So according to this model, it believes, and I think this is I'm pretty sure this is a Labrador Retriever. Someone correct me if I'm wrong. It looks like a Golden Retriever. But anyway, with some certainty, with 89.47% prediction, it does believe that this is a Labrador Retriever. And we can also see what the next 4 options are. So Golden Retriever, so that's probably close. And it looks like another kind of retriever. The tennis ball is kind of funny. It sees a dog and, oh, this is a tennis ball, which makes sense, kind of. This is how easy and how quick it is to grab a neural network. Now, I know I probably glossed over some steps here, but I do want to give you that view here of, hey, I don't need to necessarily know a lot. It's okay if you're feeling a little bit intimidated from this, but you also should feel confident in the sense that I can look at a little bit of documentation and I can read through some things, and I can also implement a neural network model, right? So whatever application that you're looking for, I know here we're talking about image recognition. If you want to develop your own image recognition, or maybe you have your own problem that you like to solve, I want to give you this blueprint here that says basically, hey, I don't need to know so much about how to build all those complicated neural networks. I can just use one that's given to me, right? These are all different neural network models that you can grab on a whim and start playing around with. All right. I know I've missed some questions here. Tensor, yeah. Matrix bus information. Is your pre-processing function built in, or is it something? It's built into PyTorch, right? So the pre-processing. I think what you mean by the pre-processing part is all this, right? So in terms of, hey, this is what my neural network, my model looks like, right? So in this layer, I'm having a ReLU, a ReLU function here, and this is how many neurons I have, right? This is my layer 1, this is my layer 2, and so on and so forth, if that's what you mean. Yeah. So that is already done for you in some of these models. And that's what makes it kind of easy to use. You don't need to consider, hey, how many neurons do I need to have in each layer? Here, there's a set amount. I think there's another question. Matrix, but yeah. So what is tensor? So think of a tensor as a unit of data. So in the most basic explanation I can give, who asked that question? Muddy. So Muddy, I would say that a tensor is a unit of data that corresponds to PyTorch. So PyTorch, it takes a certain type of data and it must take in a tensor. Right? So you have different levels of tensor, but what's more important here is, hey, I just need to convert something. I just need to convert my data into a tensor of a type. It's essentially a data type for your model. These models are trained, and I can just use it. Exactly. Yes, these are all trained, and you don't need to buy cloud resources, right, and train your model that way, or have a high-end computer. Absolutely not. These are all trained, and they're ready to go, and you can use them, today. Mm-hmm. What else? What other questions do we have? So as far as content goes, again, I'm going to share this out with you all. As far as content goes, that's pretty much it. Again, just to recap, the goal of this presentation, I really wanted to have everyone comfortable with the idea of a neural network and see how easy it is to implement one. Going back to, just to recap here, going back to the math of a neural network. I know we looked at a very basic example. We didn't look at, neural networks with multiple hidden layers, right? Or activation functions. I didn't even talk about that. That discussion is more appropriate when you get deeper. But if you can understand the math that's happening behind here, you can understand a neural network. And this math, again, I want to emphasize is, where is it? Where is it? Here, where essentially we're taking a bunch of weighted sums. We're taking a bunch of weighted sums from our inputs to our outputs. This weighted sum, of course, is influenced by our weights. And how do we influence the weights themselves? Well, the very first step is just going to be picking a weight, picking a random weight. And then we're going to have the machine, the computer, figure out, hey, are we getting hotter or colder, right? And that's what I tried to show here, where the computer is going to just start making some guesses. It's just going to start adding a factor by a learning rate. Hey, I'm going to add a small number to my weight or subtract a small number from my weight. How does that get me? Does that get me further or closer to my prediction? Yeah. Yes, William, absolutely. I can absolutely. Does that mean we can skip tokenization, etc. for NLP? No, you would still have to. A great question. For NLP, you would still want to do that. You'd still want to tokenize and get rid of stop words and all those kinds of things. That's absolutely correct. How are these models already trained? Do they use something like reCAPTCHA to build an image? So these are, if you mean how are they already trained? Well, some researcher took the time to create the network, to create the layers, to create the neurons and all the activation functions behind it. Some researcher took the time and then he gave it to us. So hopefully that answers your question, Malia. Was that unsupervised ML? Yes, this is unsupervised. Neural networks typically fall under unsupervised. Think of neural networks as a type of clustering solution, kind of. It can find patterns in your data that you don't tell it explicitly, and it'll be able to tease out patterns. Yeah. What else? What other questions we have? I think we have just a few minutes here. I'd be more than happy to answer any of the questions or anything you'd like to ask. Any plans for the weekend? Man, I know I'm getting some rest. Amelia's probably getting some rest too. Right? Anyway, I digress. Right. Exactly. Yeah, exactly. Okay. I can stick around for a few more minutes, but I really want to appreciate not just Amelia for allowing me to be here, but appreciate all the participants, all your time. I really appreciate your time and your focus here for these last 45, 50 minutes-ish. Appreciate you hanging in there. Appreciate the questions. I think I put my contact information at the very top. I can put that again, but feel free to reach out to me. If you have any other questions or anything I can help with, I'd be more than happy to help out the community. It's a very special community I really enjoy. As you can tell, I really enjoy these topics and talking about them. And so I think it's really important that we gain some knowledge and see how we can apply it to the next set of problems that we're going to have, right? Or maybe the current set of problems, right? So how would reinforcement training fit in? Reinforcement is going to be a little bit different. That's a good question. It's going to be, yeah, reinforcement is slightly different. It's outside of supervised and unsupervised. Yeah, that's a little topic. We can get into that. We can get into that for sure. Is neural network a good idea? Increase idea for a regression, which are not. Is neural network a good idea? Neural network is a great idea for general classification problems. Although it wouldn't be the first model. Who asked that? Mehdi. It wouldn't be the first model I'd choose. I'd probably go with like a simpler, like a log model. But certainly, neural networks are good for classification. Yeah. Is neural good increase accuracy for classification? Yeah. It's funny you mentioned that because for classification specifically, I would probably choose a log regression first, just because it's a simpler model and there's not a lot of black box type stuff that's going on. So I would be more comfortable sharing that, for example, with a client versus a neural network. It's a bit of a black box. Yes, you have all these layers. Yes, you have all these neurons, but it's hard. It's very difficult to articulate. And here's what I mean. It's very hard to articulate to a client or an end user, hey, what the heck is happening in here? It's very difficult. It's hard. Yeah, the weight for this one is being tuned and it's going to here. And no. You're going to lose your audience really quickly. So this is what makes neural networks a bit of a black box. If you've heard that term, a black box. Mm-hmm. Is transformer hugging face considered? What's hugging face? What's that? Man, I feel old. I don't know what that is. Always start small. Yes, I agree with Chris. Yep, I always agree. I always start with a simpler model. If we're talking about classification, my go-to of course, is going to be a log regression. I'm going to start there and go from there. Mm. Yeah, I agree with that, Sean. Mm-hmm, mm-hmm. Keep it simple, stupid. This is my philosophy. I just keep it simple. All right. Is it a depot for? Oh, okay. Thank you for sharing that. I didn't know what that was. Okay. Mm-hmm. All right. Again, I really want to appreciate all your time, all the participants, and I want to thank you, Amelia, again. Can't thank you enough for hosting me and having me. Hope everyone has a great holiday weekend and stay safe. Thanks, everybody.